Hello, my name is Karan, and today I'll present our work on modeling and strategy synthesis for robotic manipulators operating in presence of humans using stochastic games. This is a collaboration with Rice University, specifically Andrew Wells. Consider a robot as shown in the picture. The robot is tasked with spelling ARIA lab either horizontally or vertically. We also have a human that can move objects around. Now let's see a rollout of a strategy computer using prior works. For the robot to successfully finish the task, it needs to reason and react to the changes in the environment caused by the human. As you can see, the human intervenes. The robot does reasons and reacts to the changes and eventually completing the task by placing the blocks horizontally. These interactions can be naturally modeled using a two-player game where the human is viewed as a strategic agent and thus winning strategy is synthesized. But to ensure winning strategy always exists, prior works have either assumed a bound on the number of human intervention or the human moves are constrained to ensure task completion. For example, the human can only move blocks to the left as shown in the figure. To mitigate these issues, another line of work models the human moves as non-determinism using MTPs. This allows us to relax the assumption on human intervention while incorporating prior knowledge on human action preference. Thus, the optimal policy is to finish the task vertically. Unfortunately, this approach does not allow us to model a strategic human. Both frameworks have obvious drawbacks. In reactive synthesis, strategies that are good for the worst case may exhibit suboptimal behaviors in probable situations. In probabilistic synthesis, strategies that are good for the expectation may be terrible in some unlikely but possible situations. To address these limitations, in this work, we explore stochastic games. Stochastic games are more expressive than two-player games and MDPs. Stochastic games allow us to treat human as a strategic agent while incorporating prior knowledge about human action. While stochastic games have been well studied before, they have not been explored for robotic manipulation domain. At the high level, the approach we take is as follows. We first convert the continuous manipulation domain to turn-based stochastic game. Next, we use Prism games as a probabilistic model checker to synthesize optimal strategies for the robot. First, we'll see how to discretize the continuous domain and construct an MDP. This abstraction can then be extended to construct a stochastic game. To discretize the continuous domain, we first identify all objects of interest. For our toy example, say we have red, yellow, and blue blocks. Next, we group locations as per locations of interest. These include end effector location and not, and locations L1 to L4 where the objects can be placed. A state in the MDP is a valid configuration of all objects at some location in the workspace. The MDP contains a set of all states that correspond to all possible valid configuration of the objects. Then from every state, for every action, we check if the state satisfies the preconditions corresponding to the robot action. Here, from the initial state, under the grasp action, the robot can grasp either the blue block or the yellow block. Next, the robot can then place the blocks in the end effector. The non-determinism in the MDP stems from human actions. Here, the dashed edge represents the possibility of human intervening and moving the blue block. AP is the set of task-related predicates that are true or false. L is labeling function that maps each state to an atomic proposition. Finally, we assign the initial state corresponding to the initial configuration of the workspace. Next, we will see how strategic and stochastic elements of the human and robot can be combined to form a two-player stochastic game. To capture a strategic human, we augment the abstraction with environment states corresponding to human. The game, starting from the initial state, evolves in turns. Once the robot finishes grasping a block, the game evolves to human state in square. The human actions are every possible move of the objects in the environment. The transition relation delta is obtained from likelihood of human actions. This can either be predefined or computed from prior demonstrations. As mentioned earlier, in reactive synthesis, a limit is placed on the total number of human intervention to ensure specification is realizable. Here we consider two alternate models for the human intervention. The first one is a deterministic one, where we have a ratio of human to robot action. For example, a ratio of 2 means that the human can intervene twice for every robot action. The dashed edges on the right correspond to human moving objects twice. The other model uses a probability of handing control from one player to another. From every environment state, there is a non-zero probability that the human will not intervene in it. This is shown by the dashed edge. This avoids setting a hard limit on action for either player. Once the stochastic game abstraction is constructed, we pass it to Prism Games, a synthesis tool for strategy generation. For synthesis, we take the composition of the game with the DFA corresponding to the specification. To synthesize optimal strategies, we use value iteration algorithm. The default approach to construct stochastic game is by using the Prism modeling language. Our model is flat, that is, it is less structured, it suffers from scalability. The built-in parser reads the model file and constructs a matrix-based representation of the game. Found this parsing phase to be a bottleneck. Thus, in our approach, we bypass the parsing phase and add a functionality to input the matrix representation directly to Prism games. Let's consider a simple pick and place domain. We benchmark the original implementation with a modified implementation. We first fix the number of objects and vary the number of locations. While the original implementation does not scale beyond 8 locations, ours can scale up to twice as many locations. For the 3-object, 8-location scenario, we see 1,000 times speed up in model construction. We observe similar trend when we fix the number of locations and vary the number of objects. Since we do not make any changes to the synthesis algorithm, the computation times for synthesis remains the same. On this slide, we show the model construction and synthesis times using our implementation. Note that the total computation time still grows exponentially for both the scenarios. Finally, here's a robot demonstration. We consider the tic-tac-toe game where the robot is unaware of the level of expertise of the human and suffers from the trembling hand phenomenon. There is a 5% probability of failure for each player. Let us see a rollout of a strategy for the robot with only the human player misplacing their marker. Here, the human initially misplaces his marker in the action. Instead of placing on the top left, the human places it in the middle. Notice how next the optimal action for the human is to place it on the top, where there is less chance of misplacing the marker. Finally, the robot ends up winning the game. For more details and robot demonstration, please come to our poster session. Thank you.